Hello everyone, my name is Florian and today I'm giving you my PhD presentation about neural jump ordinary differential equations. So let me start with the outline. First, I want to speak about the general neural jump ODE framework of the first two papers. Then I want to continue speaking about generalizations to noisy observations and the dependent observation framework. Afterwards, I want to dive into long-term predictions with our framework. And finally, I want to speak about neural jump ODEs applied to input-output systems. So let me get started with the problem setting. So overall, what we consider is to have some cat-like RD-valued stochastic process X. As for example, we see here a one-dimensional process or a path of a process in the plot below. We see this can have jumps. And of this process, we assume that we have a training set of n independent realizations, so independent paths of this process, which are observed at a random number of observation times nj, and the observation times are t1 up to tnj. They are also random themselves. So we see we can have larger differences between two observations or just small time differences. And for a different path, we can have different number of observations. Additionally, we can have an observation mask. So this is just a vector with entries in 0, 1 telling us which of the coordinates of the process in a multidimensional settings are observed. And then the goal given this setup is to learn the optimal prediction, where optimality is meant in the L2 sense. And theoretically, we know what the solution to this problem is. Particularly, this is just given by the conditional expectation. And this optimal prediction we want to learn, we mean in a continuous in time sense. So what do I mean by this? Is the following, that for example, if we are at time 0.2, we want to learn the optimal prediction given all the information that we have in the past. So this would mean those two observations that we have made before. And then continuously in time, we want to continue predicting. This is what we see here with the green dotted line. We want to predict given the information that we have, the optimal prediction of the process. And then as soon as we get new information, so a new observation arrives here, we want to take this into account. And so we see the new observation that arrives leads to a jump in the information, and this jump in the information usually also leads to a jump in our prediction, as we see. So this is what we would like to learn. However, in this fully data-driven setup, it's not clear how to learn or extract this conditional expectation just from the data we see. And this is what our framework will do. So the assumptions that we have are, first, the underlying process X is independent from the observation framework. And the observation framework means the number of observations n, the observation times ti, and the observation masks mi. Moreover, we assume that the jumps of the underlying process X do not coincide with the observation times. And we will see, or what we can say is that the first two of those assumptions, they can be lifted. So the first one we will see later in this talk. And the second one, I just want to give a quick explanation how this can be lifted. In particular, if we assume at the jump time, if we have an observation at the jump time, and we assume that we do not only observe the value after the jump, but also the value before the jump, so we observe what the jump itself is, then we do not need the second assumptions. Moreover, we need some integrability assumptions of X, which I do not want to specify further here. And then we need some regularity of the process X hat. So this is the conditional expectation process. In particular, we want that it can be written in this form here. So in principle, we want that there is some function, capital F, describing the conditional expectation, and that this function is differentiable in the first coordinate t, such that by the fundamental theorem of calculus, we can write it in this form. And we see that in general, this is a very general setting, which allows for irregular observations, missing values, jumps in the underlying process X, and path dependence of the process X. And we did not assume any knowledge of the underlying distribution, so we only observe paths of the data, but we do not know what the underlying distribution is. So we want to come up with a fully data-driven forecasting framework. And to do this, we need some ingredients for our model. The first are recurrent neural networks, so the most known machine learning framework for time series, where a latent variable h is defined kind of discretely, and the latent variable hi is updated with new information xi plus 1 through a recurrent neural network cell. So this is just a neural network to output the new latent variable hi plus 1. And we see that this framework is fully discrete. So if we want to put this so if we want to say that the I corresponds to time, then we would say that we have regular observation times. So clearly this cannot deal with the irregularity of the data that we have on the one hand, and also cannot give us continuous in time predictions. So we need a second ingredient, which are neural ordinary differential equations, where a latent variable h is now defined continuously through time through an ODE, which is driven by a neural network f theta. And what we see here is that as soon as the neural network f theta and the initial condition h0 are fixed, the entire evolution of the latent variable ht is predetermined, meaning that this cannot deal with new observations which arrive during our time interval. So this cannot adapt the prediction based on those new arriving observations. So kind of the clear thing to do is to combine those two parts, which was first done in the ODE-RNN framework. So now the latent variable is defined between any two observations by a neural ODE. And at an observation time, we use an RNN to update the latent variable. So we see that now the latent variable from time hti minus, so just before we have the observation, to time hti. So this is really the jump. This jump is given through the RNN cell. And additionally, we use one more ingredient to deal with the path dependence of the problem, which is the truncated signature of the path. And so the signature, this is just a transformation of a path to give us in some sense a feature vector. This is truncated since the signature itself is infinite dimensional, and this is used as a feature to deal with the path dependence. So now we can specify our Neural Jump ODE model framework, which is given similar to this ODE-RNN framework as displayed here. So we define the latent variable now given by capital H, written here in this SDE form, where we have the first part. This is the neural ODE part, so F theta, the neural ODE, driven by dt. And the second part here, this is the RNN cell, so the n, this is just the process counting the number of observations that we currently have. So we see this jumps by 1 if we have an observation, and otherwise this is constant, so this term just appears at an observation time. Additionally, we look here at the outputs before and after the jump, which are just given as a readout map G applied to the latent variable H. So G here is also just a neural network, which can often be chosen just as an affine map. And then the second important part for our model design is the design of the loss function, which we see here, which basically consists of 2 terms. So the first term compares the model output after the jump to the actual observation. We multiply here with the observation mask, so to make sure that we only use the information of x, which is actually observed. And this first term means or pushes the model to actually jump to the observation, so after having this information. And the second term, this compares the model output before the new observation, so before the jump, to the actual observation that we have afterwards. And here, if we forget about the first term and just consider the second term, we see that this is squared. We take the expectation. So we see this is really the term which is minimized by the conditional expectation of x. So this kind of explains how the following theorem works, which basically states that the output of our Neural Jump ODE model converges to the L2 optimal prediction x hat, so this is the conditional expectation, as the number of paths n and the network size and signature level m increase to infinity. So one word about the convergence. So the convergence that we claim here, this holds with respect to the pseudometric which is given here, which basically compares 2 processes at the left points of observation times. So these pseudometrics, they kind of incorporate exactly the information that we get through our training data. So what this means is that with this metric, we cannot make any claim about time intervals where we never have an observation. So those intervals, since we do not have training data there, we simply do not know what happens there. And in line with this, we cannot, or whatever we learn there, we cannot verify that it's good. And this is kind of displayed in this type of convergence metric. On the other hand, we see that if the observation times are nicely distributed over the entire time interval, and with nicely here I mean that they have some density which is lower bounded by a positive constant, then we get good approximation in this L1 sense as is written here. So we really have kind of the integral over the entire time interval, which has to be small. Let us now consider this convergence result also empirically. So what we do here is we take some synthetic data set where we know the true underlying distribution so that we can actually produce the actual true conditional expectation for the paths as a reference value. And then we compare what we learn with our model to those true conditional expectations on a very fine time grid. And this we call the evaluation metric. And then we see that as the training size of our data set and as the network size, here displayed in different colors, both increase, we have quite nice convergence behavior, as the theoretical result stated. So now I want to look at some examples just to showcase that the model actually works well. So the first example would be data coming from a Heston model, and then we train our model on this data set, and afterwards apply it to it. And here we display one plot on a test sample path, which was never seen during the training. And what we see is that our model, given in orange, replicates the true conditional expectation very, very well. So we said that our model can also work with underlying processes which have jumps. Here, what we look at is a homogeneous Poisson point process. So this is a process which stays either constant or jumps up by 1. And again, we see that our model perfectly replicates the true conditional expectation. The same is true for path-dependent processes. So here we look at the fractional Brownian motion with a very small Hurst parameter, meaning that this process has very large negative autocorrelation. And again, we see that we nearly perfectly recover this. Finally, I want to showcase that the model also works with incomplete observations. So here we look at a two-dimensional data set with two Brownian motions which are correlated. And then in the data set, we either see the first or the second coordinate. So for example, here we observe the second coordinate, but we see that also the first coordinate is updated correctly. So far, I only spoke about point estimates. However, our model can also be used or generalized to be used for probabilistic forecasting purposes, and or let's say first for uncertainty estimation, and this can be driven further to be used as probabilistic forecast. So for the uncertainty estimation, what we can do is to look not only at the first moments, not only at x, but also at higher moments, for example, here at x squared. And then we know that the conditional variance of the process x can now be described through the conditional expectation of the second moment and the conditional expectation of the first moment squared. So this can be used as an uncertainty estimate. And for example, we did this here on a very easy data set of a Brownian motion x, where we see on the left side the prediction of x, and here the prediction of x squared. And then on the right side, we see the prediction of x together with the conditional standard deviation computed as the square root of this thing here. And by predicting phi of x for any measurable function phi, or higher moments, we can in principle approximate the entire conditional distribution of x. So we applied this model also to several real-world data sets. Here, some examples are anomaly detection in gut microbiome data of infants, the FusionNet data set, which is patient data of patients in a hospital, so health parameters of them, climate data, and limit order book data. So this would be financial data. However, in the following, I would rather to stay with the synthetic data sets because they have the nice property that we can compute the true solution and use this as a reference to compare how well our model is actually doing, which is not possible with the real-world data sets usually. So now let me come to the second part, which is about noisy observations and the dependent observation framework. So let me actually start with the second thing, which is the dependent observation framework. So far, we assumed that the underlying process X is independent of the observation framework, so N, Ti, and Mi. However, if we consider this following example of patient in hospital, we see that this assumption is not very reasonable. Because if a patient comes to a hospital, then usually the decision whether to make an observation, so whether to test certain health parameters, so for example, make a blood test or a urine test or so on, this will depend on the condition of the patient. So if the patient feels very well, then probably he can go home. However, if he's in a very bad state, then probably the doctors will decide to make intensive measurements to find out what the problem is. So what we do is to replace the independence assumption by the following two conditional independence assumptions, which basically state that the observation framework, so TKN and MTK, they can depend only on the known information that we have. So the next observation time TK can depend on everything that we have at the last observation time before. So this is the information that we have, and if it only depends on this and other things which are completely independent, then it is fine. And under those generalized assumptions, we can recover the same theoretical results as before. However, one still has to be a bit cautious, because in a hospital, what can happen is that a patient tells a doctor that he doesn't feel well. And this feeling of the patient, this would, of course, give some information about the true underlying process X. But if this feeling is not tracked, then we would kind of get information about the process X, which we use information about the process X, in particular the feeling, which is not given in the information that we have in our sigma algebra at the last observation time. So this would contradict the assumptions that we have here. So one way to deal with this would be to also track the feeling of the patient. However, this might be a bit hard in a hospital setting. So as I said, one has to be a bit careful with this. Here's one example where we actually make the observation probability depending on the last observation of X. So we see in red, this is the probability of making an observation. Here is the scale for it. And then we see again that the predictions that we get from our model are nearly perfect. So with this, let me come to the second part, which is about noisy observations. So far, we assumed that we observe the true underlying process X directly. However, often in real-world settings, we would have IID observation noise at any observation time. So what does this mean? We would have some epsilon k's, which are IID, and here we assume that they have mean 0, such that we do not observe X, but instead we observe OTK, which is XTK plus the epsilon k. And then if we revisit the loss function, we see that the first part of the loss is not reasonable anymore. Since even though we now observe the observations OTK, we still want to predict the underlying process X. So we do not want to predict the noise, meaning that here in this first term, which pushes the model to actually jump to the observation, we would basically jump to the noise, so overfit to the noise, instead of filtering out the noise. However, the second term of the loss, this turns out to still be reasonable, and even more so, we see that if we just delete the first term and only use the second term of the loss, as given here, we can recover basically the convergence result that we had before, particularly that the Neural Jump ODE converges to the conditional expectation of the process X given the noisy observations OTK. And the reason why this is true is that the conditional expectation of OTK is the same as the one of XTK under the assumption that this is completely independent and has mean zero. And here is one example where we nicely see the difference between the old loss function or the standard loss function on the left and this noise adapted loss function on the right. So as we said, using the original loss function, we really jump to the noise. So we completely overfit to these noisy observations, while on the right-hand side, we see that we filter out the noise and nicely recover the true conditional expectation of the underlying process X, given the noisy observations, which are now the blue dots, while the green stars would be the actual values of the process X. Now, having this second loss function, so this noise adapted loss function, the following question arises, which is that theoretically, this loss function is also valid in a setting where all the noise terms epsilon k are just zero. So the question is, which loss function should we then use? And while theoretically both are equally fine to use, empirically, what matters is the inductive bias, because we only have a finite training set. So the inductive bias that we get through our training setup, this is really important. And if we are in the case where we do not have observation noise, then the original loss directly penalizes wrong jumps, so makes it much easier for the model to learn to jump to the observations and to, in that sense, to learn the correct behavior at observation times. And so this is easier and to learn and also faster to learn. If we are in situations with small noise, of course, then it's kind of a trade-off between this inductive bias of learning the jumps and the theoretical guarantees that we get from the noise adapted loss function if we have observation noise. And what is decisive in the end is the ratio of the variance of the noise compared to the variance of the data. And we tested this here on this FusionNet data set. So this is this real world patient data data set where we artificially added noise to all the coordinates and compared the original versus the noise adapted loss function. So without any artificial noise added, we see that the original loss leads to a better evaluation metric by a little bit. And while the loss is while the artificial noise is increasing, the noise adapted loss function only increases by very little and linearly, while the original loss function really starts to explode as the noise level is getting larger. So in the end, if we have very small noise, this would mean that it's not really visible compared to the variation in the data. Still, the original loss function would be preferred. However, as soon as the noise is getting larger, we want to use the noise adapted loss function. So with this, let me come to the long-term prediction part. So far, we only looked at predictions of the kind where we used the current time t, we used all the information that we had up to the current time. So S would be equal to t. However, we can also ask ourselves, okay, can we also predict further into the future? And for this, we look now at x hat ts, where we predict xt given information only up to some time prior to t S. And if we revisit this plot, then this would, for example, mean that at time 0.2, we want to stop using new observations as input. So we would want to use only what we have had until time 0.2 as input, and then predict for the rest of the time interval. Meaning that clearly those observations which we make here, we don't want to use them as new inputs to the model. However, we still want to use them in the loss function because still those are the true observations which we would like to replicate with our model as good as possible. So we still use them in the loss function, however, not as inputs. And to make this work, we need to adapt the training framework in a way such that we kind of do not always use all the observations as input to the model. And one way to do this is to simply randomly mask observations which are used as input by, for example, using just the probability between 0 and 1 to decide whether it's used or not used, which leads to a certain type of data augmentation. And clearly in each pass through the training data, so in each epoch, we can redraw those variables which say whether we use a certain observation or not. So we get all the different combinations of points or of observations used and not used as input. And using this adaptation to the training framework, we can recover the same convergence theorem, so that now the Neural Jump ODE converges to this generalized conditional expectation x hat ts for any t and s. And here are two examples where we showcase this. First one is on a data set, on a chaotic system data set. So this is a deterministic data set, so this would be a double pendulum, where actually given the starting point, the behavior is deterministic. The second one is a geometric Brownian motion data set with very dense observations in the data set, such that learning in general on this data set, we would never see a longer time span without any observation. And in both those data sets, we see that the model doesn't learn to predict far into the future because it's used to having an observation after a certain time on which it can, in some sense, recalibrate. However, if we use this adapted training framework for long-term predictions, then we see that now our model nearly perfectly predicts over the entire time interval. And with this, I want to come to the last part, which is applying the Neural Jump ODE framework to input-output systems. So now what we assume is that our process X is divided into an input process U and an output process U. So we want to use the input process U as the information we get to predict the output process U. So clearly the Neural Jump ODE model will only use U as input now, and the output will try to replicate the process. So if we now consider the loss function, and clearly we need to change here x to v. However, we also see that squaring outside doesn't work anymore. So we need to change the loss function in the following way, that now we have to square both terms separately. And this is the case because now the first term doesn't vanish in general anymore. Because before we tried to predict x, which we observed itself. So of course, after the jump, we should perfectly predict it such that this first term vanishes. However, now that we only have the information from u and try to predict v, this first term doesn't vanish anymore. And since this doesn't vanish anymore, this changes the behavior of this loss function, and in particular, it changes what process is optimal. So if we square outside, as in the old original loss function, then the conditional expectation of x, or of v in that case, is not the true minimizer of this loss function anymore. However, using this adapted loss function, it is. And this is what we recover, that the Neural Jump ODE converges to the conditional expectation of v given information from the process u. So now I want to show some examples of using this input-output setting. The first one would be standard stochastic filtering. So here we have some unobserved signal process, which we call X here, to stay with the standard filtering notation. And then we have some observation or sensor process Y, which in our case would just be X plus a Brownian motion W, and X itself would also just be a Brownian motion. And then clearly the input process would be the observation process Y, and the output process would be the unobserved signal X. So from U, we want to predict V. And if we do this and compare the two loss functions, here on the left the old and on the right the new loss function, then we see that with the old loss function, our model learns here somehow a weird behavior. And this is exactly what it learns here is exactly this different optimizer to this old loss function in this setting here. So in terms of the old loss function, the Neural Jump ODE model prediction is actually better, so it leads to a smaller loss, and this is significant, even though the difference is small, than the true conditional expectation would lead. So we really see the conditional expectation is not the minimizer of the old loss function, because the Neural Jump ODE learned something which is performing better. So what we learn from this is that the loss function is very important, because here with the new loss function, we see that we perfectly recover the conditional expectation. And on the other hand, we see how powerful our model framework is, because it manages to exploit those small differences in the loss function. So it's really just where to put the square. And we see that this makes such a big difference. So with this, I want to come to the last part, which is about classification. So what we look at here is some finite state space model S, which takes values in a state space with states S1 up to SNS. And given some arbitrary input process U, so this would usually have some information about the state space process S, but in principle can be arbitrary, we would define the output process V as the process with the indicator, so the J coordinate of V would be the indicator that the state's model is in the state J. And why do we do this? Because now we know that our model can learn the conditional expectation of V, which is just given by the conditional probability that the state space model is in state J, given the information that we have. So this conditional probability, this really is the true optimal solution to the classification problem. And here in one example, we use as underlying process, we use just a Brownian motion and define the state space model to be to have the values 1 if the Brownian motion is larger than 0 and 0 otherwise. And then we see that using our model, we recover the true conditional probabilities of the states perfectly. So we see we can also use this framework using an MSE type loss function for classification purposes, which at first sounds probably a bit weird. However, we really see that we recovered the optimal solution with our framework, which is very nice. So with this, I want to come to the conclusion. So we have seen theoretical convergence results for our Neural Jump ODE model to the optimal prediction. We have seen adaptations for different settings, so for dependence, noisy observations, long-term predictions, and input-output systems. And throughout the talk, we have discussed 3 different loss functions, and here I list them by their inductive strength. So what I mean is that if all assumptions are satisfied, then the original loss function, this is the strongest one from its inductive bias speaking. So this should be preferred. The second strongest one would be this input-output loss function, and the weakest is the noise-adapted loss function. So depending on which assumptions are satisfied, the loss function should be used in this preference. We also saw that empirically the model works very well, and through the experiments that we showed, we saw that there are many potential applications to forecasting tasks, filtering tasks, also parameter filtering, or online classification tasks. The outlook, what we are currently working on, is a functionally valued version of this Neural Jump ODE and generative versions of the model. So with this, I want to thank you for your attention and for watching this video. Here are the references used throughout the talk, and hope to see you at some point.